Thank you very much, Daryl. Thank you, Rich and Andy. For EGI to be better connected to the university, we definitely need support and cooperation from, of course, the Vice President's office, as I said, who leads EGI, but also from the two colleges that EGI is most closely associated with, the College of Engineering and the College of Mines and Earth Sciences. So I, again, would like to thank Andy Weirick, Richard Brown, and Daryl Butt for taking time to talk to you. And this is not just a one-time event. And I think what we would like to highlight here is that these three units, I mean, EGI and the two colleges and the Vice President's office will all work collaboratively to solve problems that are of relevance, I think, to the industry. And so that's basically what we wanted to highlight in this opening session. So I'll take that background and give you some information about where EGI has been and where EGI would like to go in the next several years. So most of you probably know the Egi history, but for those of you who don't know, Egi did start in South Carolina, University of South Carolina in 1972, and moved to Utah in 1995 in that time frame. As it came to Utah, it grew slowly to one of the largest university-based E&P consortiums in the world. As it did that, EGI scientists worked in all 7 continents and in over 70 countries. And over the last 10 years or so, since about 2011, 2012, EGI, in response to the need of the industry, became or created one of the largest combined shale science and engineering teams. And the EFRC that Professor Butt mentioned was in some ways a reaction to that need, but it of course went very basic in terms of the type of research was conceived. EGI has again very strong international presence, as you can see here, scientists from, of course, all over the world, but also just working in these 70 countries, as I mentioned, and that really provides a unique advantage as industry collaborates with EGI. So there are projects in these countries, both onshore and offshore, and particularly offshore, which, since it takes so much more logistics to conduct these projects, EGI has the expertise and experience to have done that. And over these years, EGI has delivered, I think now, over $800 million in research to sponsors. So obviously we are coming out of a pandemic here. As last year, I guess, was almost a blur for most of us. I'm wearing a tie for the first time, I think, in 2 years or something. That's what it feels like. But we are basically following the university guidelines for teaching and research activities. Currently, we are in what is called limited research activities, but they're slowly growing. And currently, with most of the people, or at least I think 60% of the people in Utah vaccinated in that age group, the classes are expected to be in person in fall, or at least 75% of the classes are expected to be in fall, in person. And as a result, we believe that the research activities will also become more and more normal. As this happens, we definitely would like to conduct research at EGI safely and as directed by the health authorities and by the university. And I would like to say that in general, the state and the university have managed that pandemic reasonably well, and with the least amount of effect, I think, on the community. And on top of this, we have had leadership transition that The Vice President mentioned, the two deans mentioned as well. And I would like to take this opportunity to thank our former director, Dr. Raymond Levy, who created a strong EGI, and for 20 years of distinguished service to EGI. One takeaway message that I want, though, for the industrial folks who are attending this meeting is that EGI is basically open to business. We are committed to engaging with our industrial partners in solving problems that are important and relevant to you. So here is our mission statement. I'm not going to read all of it, but basically it says things that the two deans have highlighted, which is to conduct research in energy resources in a sustainable manner and look for opportunities as this energy transition happens in renewables and in other cleaner or low carbon energy technologies. EGI is one of the few, or probably the only, large institutes in the world that does this cross-cutting research of geothermal, hydrocarbons, and carbon sequestration or carbon management. And this gives us a unique strength, I think, to lead in this energy transition that we are currently observing. Rich Brown showed the expenditures for the college, so you get some perspective of, so we are in the order of 100 million or so for the College of Engineering. So you can see here the EGI research expenditures are of the order of about $10 million per year. So we are a significant portion of the university research, and I believe this will continue to at least be sustained or even grow because of the because we have currently ongoing large projects like Forge and some of the carbon sequestration projects under Professor McPherson. So not only is the research strong, but EGI scientists excel in their scholarly activities too. So as you can see here, just like we have people working in interdisciplinary aspects of geology, engineering, material science, you see publications in that space. You see publications in geologic journals, in engineering journals, and in high impact journals like Nature. These are all from EGI scientists. So our goals are pretty simple in some ways, is to establish EGI as a world leader in sustainable and efficient production of energy and water. Water will become more and more important as a resource, particularly in the West. And we would like to use our expertise in subsurface technologies to work in those areas. EGI is a part and parcel of University of Utah. So we must have a dynamic and thriving research and academic community at EGI for EGI to succeed, which means that EGI needs to be connected to the two colleges and beyond. So we are looking at, of course, College of Engineering and College of Earth and Mines and Earth Sciences, but also College of Science, College of Education, and Business as EGI continues to grow. And one of the things that EGI offers to the industry are trained students and postdocs. And we would like to continue our education mission to bring you the best in best students in engineering, geology, and related disciplines. So now I'm going to go over the three areas that we talked about. As I said, these areas are cross-cutting in a lot of ways. So I'll start with the hydrocarbon program. So once again, you see here the range that EGI offers. You see projects ranging from offshore, large offshore projects like EGI Oceans, Gulf of Mexico type of projects, and very large portfolio of projects in shales. Again, very few geologic institutes have this range that go from onshore to offshore to conventional to unconventional basins. So we have talked to the advisory board. By the way, I think a number of our advisory board members are participating today, and I would appreciate their advice and participation. We have talked to them, and based on the advice and feedback that we have received, these are some of the areas in which we will continue to expand in the hydrocarbon space. Is to look at, we'll still continue to look at targeted exploration areas worldwide based on the needs of our members. Rocks are our business too, right? So in that sense, we will continue to look at characterization and understanding of these rocks in detail. We have understood that integrating geology and engineering to understand producibility is important. And as a result of that, we will focus on reservoir dynamics and fluid flow and how geology and geologic environments impact those type of issues. And in doing so, even though oil and gas will continue to dominate, and currently we use about 70% of our energy, 70% of energy comes from petroleum. Producing this efficiently and sustainably over the next 2 to 3 decades is going to be very important, and we would like to seek partnerships in the areas of this type of research. The two pictures that you see here is one that shows a reservoir scale work that we did, so published in AICG journal, by the way. And the top image here is a 3D printed shale, actually, that came out of a very high resolution imaging that we conducted here at EGI. So again, you can see the range of activities here, scale ranging from nanoscale all the way to the reservoir scale. Moving on to geothermal research, as Rich Brown pointed out, we would like to support and highlight, forge and explore opportunities in geothermal space. And in the next session, Professor Joe Moore will talk about forge in detail. It is really one of a kind project, and successful implementation of forge will be a game changer, not only for the university, for the Department of Energy, but for the world at large. And using that as a baseboard, we would like to make University of Utah an international geothermal hub. Of course, there are a lot of cross-cutting themes there, right? Such as fracturing, understanding induced seismicity, fluid production, heat transfer, and those type of issues we would like to understand and use them in other applications as well. Low carbon future is the future of the world, right? And so we would like to continue our expansion in carbon sequestration and carbon capture and utilization. So that will also become more and more important as we want to use carbon for making useful products. And there are a lot of faculty on campus who have started research in that area. In fact, I have a project with ARPA-E looking at carbon fixation in agricultural fields. So those type of research projects will become more and more important. And natural extension to these is to essentially limit and minimize pollution, such as ozone and particulates in Utah, but in all other basins, methane emissions, flaring, for example. And there are a lot of initiatives here in the oil and gas business that we would like to capture. We would like to do this under the umbrella of data science, as Rich mentioned, because this is not an option anymore. It is mandatory that we work in this in this type of a mode where all our data is available to companies in the platform of their choice. And we have joined OSDU. It used to be Open Subsurface Data Universe, but now I think it just goes by OSDU. And we'll be developing applications there that would plug into the data space that the companies have. And a couple of applications are already in the cards. And we will be talking more about those during the meeting, but also exploring that further with you if you have interest. As we do this, we are going to work with stakeholders on campus like the data center, Ski Institute. And again, we are a university, so we want to develop an educational component to this. We would like to have students in geology, engineering, this background, the data science background, as they graduate in their domain expertise, in their areas of interest. And the Egi is definitely interested in pursuing this, and we are investing currently in this space as we grow. And then there are other complementary areas like hybrid energy, where we are looking at optimization, and one of our faculty members will talk to you about this tomorrow. Minerals, particularly rare earths, we have started a small program right now in this, but university recently received a fairly large grant from Department of Energy to look at rare earths in coal basins. We are then looking at energy storage, which is becoming a linchpin technology, kind of. Pollution control, as I mentioned, nuclear energy, and then water, as it becomes more and more important in terms of conservation and usage. So what does partnering with Egi really mean, right? I mean, you can be a member and have access to all the data, all the projects that we conduct, have conducted, over 1,000 of them now. Then you have opportunities to create jointly funded projects either by yourself or with partners within the university. You get a table here on federally funded projects, right? You are at the table where you interact with our scientists and our principal investigators in creating or directing the projects in some ways. That gives you an opportunity to interact with a diverse group of faculty, scientific staff, and postdocs. And then some of these can actually come and join you to help you in solving your specific problems. We have some of the best sophisticated equipment, I think, in the world. You have access to that type of equipment and services. And as I mentioned, this is something unique to Egi. You get this expertise in navigating international locations, which can be quite tricky, both in terms of data management and in understanding the politics of the situation. So this is on our website. You can take a look at this, what membership to Egi really offers, but we'll take this up one-on-one with you as we look at opportunities with you. And that basically concludes my presentation. I think we are right on time.
Thank you, Milan. My name is Joe Moore, and I am the principal investigator of the FORGE project, Frontier Observatory for Research in Geothermal Energy. And this is an international laboratory for geothermal research. Well, can you imagine being able to generate electricity or heat buildings anywhere in the world, anywhere you wanted to at any time? Well, we think it's possible. If we think about the amount of heat that's beneath our feet, say between 2 and 6 miles, tapping even 2% of that heat would provide more than 2,000 times the yearly energy needs of the US. This is not a new idea. It was originated in the 1970s, and there have been more than a dozen hydraulic stimulations around the world, and you can see them on the chart. The results have been, I'd say, disappointing. To date, there's been no commercial size EGS system developed, and tracer data show that only a small volume of the seismic clouds that are produced had interconnected permeability. Geologic observations indicate that relatively few fractures operate in these systems despite large seismic clouds indicating large stimulated volumes, and the flow rates are less than economic. They're less than 40 liters per second. What we're looking for, if we go to gallons per minute, is about 2,000 gallons per minute. All right. So the Forge project was started in 2014 to develop tools for creating a reservoir in granite where temperatures exceed 350 degrees F. Unlike previous EGS projects that attempted to stimulate long sections of open hole, Forge plans to stimulate fractures behind casing using oil and gas technologies. This will require advances in stimulation and well completion techniques, tools and zonal isolation technologies that can withstand the high temperatures, and techniques to manage and modify the native stress field while minimizing induced seismicity, a critical issue anytime we do hydraulic fracturing. Okay. Although we've worked with a number, in fact, virtually all of the oil and gas service industries, and we're told fairly often that the oil and gas works at the temperatures and in the hard rocks that Forge is, we have had tool failure virtually with every tool we've tried. Here's some examples of a worn tricone bit. We're using PDCs now, stabilizers, damaged jars, packers, and bridge plugs. Nearly better than 95% failure rate. So tools that withstand the high temperatures are required. Conceptually, the process of creating a reservoir is really quite simple. After drilling the injection well, water is pumped into the well to hydraulically stimulate existing fractures. And that's drill the first well on the left. As the fractures open, and we're looking primarily at opening existing fractures that hopefully are optimally oriented within the current stress field, they release energy, and the location of the seismic cloud that forms as this energy is released will be mapped using strings of geophones in deep wells, fiber optic cables, surface and shallow borehole seismometers, and surface nodal arrays. The production well is then drilled into the fractured volume defined by the seismic cloud. And energy from the fluid discharged by the production well can then be extracted at the surface to generate electricity or for direct heating. As after the fluids are cooled at the surface, they re-injected to heat up again, and this is a continual cycle of re-injection, production, and use. Somewhat different than the typical fracking environment that we find in the oil and gas industry. Okay. The Utah Forge site lies in south central Utah, 220 miles from Salt Lake City. And it's the transition between the Basin Range and the Colorado Plateau. This is an area of active normal faulting and extension. The map shows our key partners from around the world. They include private companies, some oil and gas companies, national laboratories, and government agencies. The site is located in Utah's renewable energy corridor, 10 miles north of Milford, which is a rural town with a population of about 1,400 people. The site is nestled between a solar field and wind farm on your left and the Blundell geothermal plant on the right. Another geothermal plant and a biogas facility are located about 10 miles south of Milford. The strengths of this site are many. There are no endangered species, no sage grouse, no prairie dogs, burrowing owls. There's no nearby human activity. And the reason for that is there's no potable water at this site. The water has chemicals in it that are hazardous to your health. These are chemicals that are naturally found in the water. So they can't be used for human consumption, can't be used for agriculture or grazing. The area has a low potential for induced seismicity and a low potential for natural seismicity. The seismicity has been monitored since 1981, And there have actually been no events on that forge site. The site itself is located on state land, Sittler land. The geology of the area is dominated by tertiary granite that's shown in green, and this forms the core of the mineral mountains. The red and purple rocks were placed around 750,000 years ago, and these are rhyolites related to a still cooling pluton at depth. The black dots are wells. Wells east of the Opal Mound Fault are production and injection wells, and they tap a 500-degree F reservoir. The three panels on the right are core samples from the forge wells, 16A. Top two are granites, and the lower one is a Precambrian metamorphic rock. The contact between the granite and the valley fill is a nearly planar dipping surface, approximately dipping 20 degrees to the west. This contact is interpreted as a rotated, steeply dipping basin and range fault. Although faults cut the alluvium to the south, there is no suggestion from the seismic reflection data of any offset of the basin contact exceeding 50 feet or so. So no evidence of young faults within our environment. And this is important too. Temperatures within our reservoir shown by the EGS box basically range from about 400 to 500 degrees Fahrenheit. Since 2016, 5 wells have been drilled, and they're shown in white. In the next 2 years, 3 additional wells will be drilled, and these are shown in yellow. With the exception of well 16A, all the wells are vertical. They range from about 1,000 feet to 9,000 feet. Well 16A was deviated in the easterly direction, approximately perpendicular to the maximum horizontal stress. And its trajectory is shown by the dashed line. It will be used to inject water into the reservoir. 16B will be drilled approximately parallel and above 16A and will be used to produce the reservoir fluids. If you look carefully, you can see a few windmills in the back between the yellow 16B and the 16A, and the solar field is off, further off to the left. 16A was a very important well. It was in fact the first highly deviated well drilled strictly for geothermal purposes by the geothermal industry. Typically, we drill wells with a 40-degree or less deviation. This one was 65 degrees. It's large diameter with a production casing of 7 inches. The well was drilled vertically to 6,000 feet, then deviated 65 degrees, and then drilled another 4,000 feet, with a total length of about 11,000 feet and an estimated bottom hole temperature of about 440 F. Significantly, the well was predicted to take 140 days to drill, but was drilled in about 80 days. This is significant. It was drilled with PDC bit using MSE to minimize specific energy. The reason this is so important, and it's important to the oil and gas industry also, is because 50% of a drilling project is in the cost of drilling. So if we can decrease the cost of drilling, say 50%, that is a huge impact on the cost of power plant development. All of the data that I've described, in fact, all of the data we generated is available on the Geothermal Data Repository. You can go to our website at www.utah.forge.com and see links to it. If you can't find the data that you're looking for, call me and we'll get it to you. Thank you for your attention. The project is funded by the U.S. Department of Energy, and we're pleased that they've allowed us to work on this project. Picture of the site. Thank you again. So last week.
Thank you so much. Good morning. And thanks, Joe, for a terrific overview of what I think is the most spectacular field project in the, in my opinion, history of Earth science. It's really fabulous. I'm going to focus our discussion shifting from geothermal energy to fossil fuel energy, but making that fossil fuel energy more green, so to speak, so carbon storage. And I'm going to focus specifically on our history. EGI has a long, rich history of CO2 field projects, and I want to just talk about those and lay the stage for the future. And tomorrow, one of our Rich Esser, who's also on the line today, he will talk a little bit more about the science. I'm going to touch on it. So title, source to sink, from injection to monitoring, from risk assessment to 45Q carbon tax credit applications, which we're working on a great deal now, but I won't really talk about in detail today. We do have a long history here at EGI, but firstly want to acknowledge up front what is now becoming a legacy initiative. And Al Walker, managing operations manager at EGI, was the associate director for operations, of the USAR initiative back in its inception, 2006, 2007 timeframe. And I came to EGI and the U under the auspices of USAR originally. And then also giant shout out to EGI itself, as well as all the funding. The projects I'll talk about in a few minutes are funded by U.S. Department of Energy and its National Energy Technology Laboratory. We've had NSF, EPA, and other funded projects, but the field projects, all NETL and DOE. And really, the biggest shout out is to the scholars. My greatest skill, and I think EGI's best asset, EGI's greatest asset is its people, really. I mean, we've talked about data, et cetera, but the people at EGI are really what make EGI special. And in my group in particular, I got to shout out to my group because it's the best darn group I've worked with in my almost 30 years. Just terrific. I can't say enough about them. This is a snapshot of most of them. All of them actually. And I did some editing late yesterday, and a couple have moved on to faculty posts and otherwise. And actually one of our guys defended a week before last, Alec Nelson. But the rest who you can see here are playing really critical roles. A big welcome to Rob Simmons, who joined us officially yesterday. He is I've asked him to serve as director of what is becoming known. We're forming with some others on campus, the Carbon Science Initiative, and Rob will direct that effort, and Rich Esser will serve as managing director of that effort. And it's I won't talk about that today, though. I'm going to focus on the field projects themselves. With CCS and CCUS, back in 2010, the DOE had with Chuck McConnell as its FE director, shifted carbon capture and storage CCS to the acronym CCUS, carbon capture utilization and storage. And a big focus was pushed over to enhanced oil recovery in particular, because it is the low-hanging fruit of carbon storage, long-term storage, short-term transitioning to longer-term CCS, if you will. And our projects shifted exclusively to EOR. And now, ironically, 11 years later, we're DOE and the broader community is shifting back to a bigger effort on CCS. Joe mentioned some efforts on soil storage of CO2. I think it was Joe who mentioned it. And we've had a broad effort on geologic storage, but back in 2007, 2008, we partnered with the USDA and conducted really a regional synthesis, synthesized analysis of how farming and other practices could maximize terrestrial sequestration. And really, just doesn't hold a candle to traditional, what we're now calling traditional carbon capture and deep storage. So capturing CO2 from point sources, not just coal-fired power plants, but also from ethanol plants, from fertilizer plants and otherwise, and we've demonstrated that in a couple of our field projects. And policy is really at the nexus of all of this. President Obama started new initiatives on CCS and biofuels. The state of Utah hopped on board a year later with a resolution supporting hydrogen power. And then in 2018, what I think is the most salient piece of legislation to come out of the Fed, and that was under President Trump's watch, and that is 45Q. It's an enhanced carbon tax credit that really has incentivized a flurry, I mean, literally just a huge number of new field projects. And in 2021, Rob Simmons, who I introduced a few moments ago, is working with, he's Governor Herbert's energy advisor when Governor Herbert was governor of the state of Utah. And he's got he's worked with the other states and everyone within the state and is helping keep our pulse on whether a state session, special session on carbon will come forth this summer. So we may see something new akin to 2009, but maybe even bigger come out in 2021. Okay, CO2 EOR and the potential impacts on Utah in particular. Just wanted to highlight this. EGI is in Utah, but we serve the broader US, really. I mean, that is something that Joe did mention for sure, and that is that geothermal energy has big implications for the entire planet. And we feel that our CO2 EOR work with storage, optimizing that storage piece with the EOR is key to really increasing the economic impact as well as the storage impact. So it's really advantageous in multiple ways, but we're also getting some really cool technologies to come forth. And we're in the middle, I'll just highlight one of these, is seismic imaging, working on some advanced tomography right now, which is really pretty exciting work coupled with induced seismicity analysis. All right, so our field projects over the years, we've had 6 major field projects starting in northern Colorado, 2 in Utah, 1 in northern New Mexico, and 2 in Texas. Rich Esser will talk a little bit tomorrow about a couple of our ongoing projects, including a new one in New Mexico that's ongoing that we're working with. But I'm going to highlight just those that we've led since at EGI that we've led since 2006, including RMCCS. It's the Rocky Mountain CCS. Paradox Play is actually not a CO2 storage project, but it's an unconventional reservoir exploitation maximization project. We've just finished a deep science well for that project. An injection project in Aneth, one at San Juan. I'll talk about these in a few moments. And then Farnsworth and Sac Rock, both in Texas. So Aneth was 2007. 4 of these, 3 of these were from 2007 to 2010. These were an EOR, an ECBM, and another EOR project. And then the Farnsworth project, by far the longest running, 2012 to 2022. It'll end next summer. All part of the Southwest Regional Partnership on Carbon Sequestration. $67 million in federal funding. But then again, you take that and spread that over effectively almost 20 years. It sounds a lot more than it really is in terms of conducting multiple projects. Then we also did just solely a characterization project back in 2010 to 2013, and now we're in the middle of that Paradox Play project. And they are through this southwestern region. The goal of that Farnsworth project, 1 million tons of CO2 injection and optimization of that injection, and optimization of risk assessment, its quantification, and really a blueprint for future projects. And that's we've met all of those goals, and we are in the final year of the project. Sac Rock was a phase 2, again, 2007 to 2010. Injection began in 2008. We injected with Kinder Morgan about 350,000 tons per year injection rate. And that's still ongoing, although we've stepped out of the field since then. Farnsworth is also now in far northern Texas, injection in 25 wells with new 5-spot patterns. They were added every year, but the market has driven that pattern addition rate reduced it quite a bit. But this has been our flagship project, if you will, especially when you consider that the CO2 supply for this project is completely anthropogenic, a fertilizer plant and an ethanol plant, and injection rate about 10 million cubic feet per day. So really world-class CO2 storage operation, highlighting CCUS. I'm going to skip on through these just in the interest of time. We did drill 3 characterization wells with this project. In total, as part of our projects, we've drilled 5 characterization wells over time in different states. So we've met all of these major findings and objectives. CO2 storage with enhanced oil recovery at the Anna field in southern Utah. That was about 150,000 tons per year injection rate over 3 years. And then successfully completed during our watch almost 300,000 tons. And really interesting seismic activity picture came out of this. We managed to use induced seismicity for not only monitoring, but also characterization. We identified some previously unimaged, non-imaged faults. And then San Juan Basin, the enhanced coal bed methane project that we worked with ConocoPhillips, we purchased 75,000 tons per year, but only managed 18,400 tons because of coal bed coal swelling between the coal cleats, and that really closed up the permeability. Still a very successful project, large scale for ECBM in any case. And then Aneth, Sacroc, and then large scale phase 3 Farnsworth is still ongoing, and you can see the relative locations of these projects. 2 other major field projects I'll close out with. Rocky Mountain CCS was back in 2010, 2013, an almost 10,000 foot, 9750 foot characterization well was drilled for that. Heavy focus on data and a template for characterization. And we've used that actually extensively in a new project started last year, Paradox Natural Fractures project. And we drilled a 9745 foot characterization well for really painting a robust geomechanics picture and how natural fractures form and how to optimize stimulation. And I'll just close out with the objectives of that. Really, we want to understand why this middle part of the Paradox play in southern Utah has such great production compared to the other 2 units within the play. And it's turning out to be a really interesting story. But I'm right at 14 minutes, so I'm going to close out with that and say thanks very much and happy to take any questions.
Good morning and good afternoon to those friends who are joining us from Europe. My name is Russo Sarkoby. I'm a research professor at EGI. I joined EGI in 2003. My presentation is a follow-up to the previous presentations by my colleagues, Dr. Joseph Moore and Dr. Brian McPherson. I'm going to cover somewhat different base, more focused on energy fluids and minerals. This would include hydrocarbons and also related energy sources, as well as energy supporting minerals. Do I have control on this?
Yes, sir, you do.
Okay, thank you. We are still in the midst of a pandemic, but there are already lots of discussions on the shape of the energy industry to come after the pandemic, both because of economic issues as well as environmental issues. I myself, for my part, published almost half a dozen articles on this issue, but this graph kind of summarizes the dilemma we are in. projected to, let's say, 2040. It's 20 years from now. It's not, it's really not a long period of time. I joined EGI 20 years ago. So on one hand, we will see the growth in energy demand for sure. But then we also have another trend or another expectation is kind of evolution or transition to low carbon energy. And if you are familiar with energy technologies, you would know that these two trends are not easy to reconcile. And that is where the dilemma comes in. And we believe that EGI is well positioned to play a critical role in meeting these energy challenges in terms of research and development, hydrocarbons in various sectors, renewable energy sources, as well as hydrogen power, critical minerals, carbon management, and also environmental sustainability of all these technologies. I took this diagram from a French news agency, and they had assembled lots of data from various energy agencies, I would say, mostly in Europe. So here we are at 2021, and the blue line basically shows the projection in terms of energy growth. Currently, we are emitting about 38 billion tons of carbon dioxide from fossil fuels. So if it is a business as usual, this will increase to 42 or so. But if we would like to reduce the carbon dioxide emission, depending on what the temperature we would like to have, like 2 degrees versus 1.5 degrees temperature increase in the global climate. So we will have lots of gaps. And this gap is not easy to fill, given that fossil fuels are next to uranium, have the maximum density of energy. So this is where the challenge, the major challenge, as well as dilemma comes in. I will skip this slide. It's taken from a recent publication by International Energy Agency, but basically it conveys the same story. Now, EGI is well positioned to do really frontier research and development. We have been around for almost half a century, and we have done research studies in more than 60 countries. EGI is a proven concept, so to speak. We have published close to 900 research reports from all over the world in various sectors. In terms of services and activities, again, you can refer to our website. It's a new website, I would say, and you will find lots of information. But we are basically a research institute. So we publish lots of research reports, and these reports are based on projects conducted for government agencies or consortia or even single companies. We are also developing a global database under the umbrella of iCourts. And tomorrow, my colleague Christopher Kessler and I will be introducing this database and the apps that we are planning to construct. We also have technical services. Again, today, my colleague, Dr. Brian Richardson and Dr. Drupad Bethy will introduce the technical services which we have at EGI. Again, in terms of publications, our scientists publish lots of research papers as well as book volumes. We also have a training service as well as field trip courses. again, please refer to the website for the listing of the services. And I believe that Dr. Tony Dore will introduce the list of the courses which we have currently. Here, this slide shows the main core competencies which we have in the energy field, geospatial mapping, structural geology and tectonics. That would also include the regional geology and evolution, chronostratigraphy and paleoenvironment, geochemistry, both organic and inorganic techniques, petrography, mineralogy and imaging, down to nanoscale, reservoir modeling, well logging, formation evaluation, petrophysics, as well as basin modeling. So these are the key components of research and the skills which we have at EGI in terms of energy, fluids, and minerals. Now, these are some of the projects in development. My colleague, Dr. Mikhail Nemchuk, tomorrow he will introduce his proposals. One topical proposal is on transfer margins, especially the thermal histories of the conjugate margins around the world, and also Suriname-Guyana Basin. This is a research initiative he will be talking about. Tomorrow, again, my colleague, Dr. Sudeep Kanungo, will be talking about a new research project we are planning on East Med basins. Again, another proposal is on Red Sea basins. iCourt's database and apps, again, tomorrow you will be hearing more about this. And also a Permian Super Basin initiative that we are currently developing. Yes, this Permian Super Basin initiative is based on a really a preliminary work Dr. Polish Panja, my colleague, and I conducted last year. So we took about more than 200,000 production data from more than 200,000 wells, and we filtered them to 48,000 wells, which were horizontal. And then we looked at the production data. And this is a kind of a reverse engineering approach, but we are reversing this from the engineering all the way to the petroleum systems. So in that way, there's some novel features in it. But when we looked at the production data, we noticed that there's a bimodal distribution for both oil and gas in the Permian Basin. And the shallow level wells and production from shallow levels are not even within the oil and gas generation window. So we analyzed this data, and the short story is that we believe that there is significant migration within the Wolfcamp shale. This is, by the way, all this data are for Wolfcamp. We looked at two different formations, but I'm only showing the data for one of them. So we believe that there's significant migration of oil and gas from deeper levels of Wolfcamp to the shallower levels. And this basically is also supported by the GOR, gas to oil ratio data. We have high GOR for the shallow level wells. And this kind of changes the picture for shale plays. They are not static. We have dynamic petroleum systems even within the same shale formations. Now, our next idea is to take the geoscience data as well as production data and then apply a machine learning algorithms and then basically try to characterize the sweet spots for both oil and gas using engineering data, geoscience data, and also machine learning techniques. I'm not going to go into the details of this, but basically, it's, as you know, it's based on neural network. You take the input data, you have a weight that would gives the strength of the information between the individual neurons, and also you add +1 bias to make the data work. So anyway, this is something that we are developing, and if you are interested in this line of research, please contact us and we will be more than delighted to provide more information. Now, aside from the admin as well as the IT staff, we have at least 14 scientists on the technical side, right from Dr. Milling Dev, who is the interim director for EGI. So these are some of the scientists that you can contact to get more information about our research activities. I think this is my last slide. Thank you very much for your attention and for your patience.
Hello, everyone. I'd like to talk a little bit about some of the lessons that we learned in drilling some of the forage wells and how there's reciprocal translation of technology between geothermal and oil and gas and vice versa. And as Dr. Moore mentioned, this has been sponsored by the Department of Energy, and we have many stakeholders, including folks in Milford, Sitla, within Utah, Beaver County, and special gratitude to Utah's congressional delegation. As you recall, the conceptual spirit of Forge is that we will drill an injection well, which has been done, and Joe talked about that well. We'll call it well 16A. And then subsequently, as Joe also indicated, later this summer, we'll do 3 stimulations at the toe of this well. 1 will be in a barefoot section, and 2 will be plug and perf. And then we will monitor the microseismic characteristics of those stimulations and drill a second well into it. And so basically what you've established after this hydraulic fracturing and drilling that second well is you've established a heat exchanger where you can pump cold fluid down one of these wells, let that fluid pass through the surface area of the fractures. And this is a potential advantage of this system, that you have a large surface area that you can transmit fluid through, where you have multi-stage fracturing all along the length of the well, as you would in a commercial situation, where you would have multiple stages of stimulation stages, and you're encouraging frac hits between these 2 separate wells so that you can develop this heat exchange system. And indeed, as Joe pointed out, we drilled 1 well at a 65-degree tangent, controlling that well to just south of east, and that is a direction that is in the direction of the anticipated minimum principal stress. One of the things that was really important on this well was the improvements that were developed by switching from roller cones to PDC bits. Historically, geothermal wells had been drilled with roller cones. We intentionally drilled this well entirely with polycrystalline diamond compact bits. And as you can see, we went from rates that were on the order of 10 feet per hour to rates that are on the order of 50 or 60 feet per hour with extended on-bottom time. And this was really, really a tremendous achievement for this particular well. It also identified, of course, some of the issues that need to be looked at, and we're working carefully with bit manufacturers in terms of looking at this. And one of the things that is characteristically seen with these bits in this rock is looking at rate of penetration versus time, is a rapid initial drop in rate and a stabilization of rate. And as time went on with different BHAs, and you can see we had a large number of BHAs in this well, we managed to work out some of those kinks and provide longer on-bottom times and more constant rates of penetration. The other thing that was noticeable in this well is that as we push these bits, there was a potential for rapid degradation over a number of feet. And we're working with the vendors and also with our colleagues at Texas A&M University, that'd be Sam Neunert and Fred Dupriest, to try and understand some of these issues and improve them for future drilling. We also had a very successful reservoir surveillance program that went on, running formation microimager and ultrasonic borehole imaging, as well as quad combo runs. And this is particularly important in these reservoirs for identifying natural fractures, because natural fractures probably play a substantial role in geothermal engineering. And these wells we ran either through bit, as I'll describe in a minute, or we taxied them in, and the taxi worked really quite successfully, as did the through bit technology. And this is really something that if it's not being used in horizontal wells now, really has a future in these wells, where you can eliminate some of the liability of running tools in horizontal completions, that basically using a through bit technology. As you can see, there's a dipole sonic interpretation in the background, but the insert shows the concept of a bit with a hole in it, and that bit is run in on tubing to the TD for logging, or a little above the TD for logging. Then the logging tool is pumped down, it's pumped through the hole, it latches into the bit, and then for a short period of time, you have a wireline connection with the bit. The advantage of this is that you can be circulating full time, and you can be reducing the bottom hole temperature, and you're also protecting the logging tool from an open hole environment. And so basically you disconnect after you've latched in the hole and made sure everything is functional. You disconnect the wireline, it's a wet connect or wet disconnect, and pull that out of the hole, and then you log out of the hole on memory. And this worked extremely well in terms of the situation, and has real opportunities elsewhere. And this allowed us to generate FMI data that was particularly useful for coming up with developing discrete fracture networks in this wellbore. And so we went through this effort, and it was a particularly successful drilling and logging operation that will allow us to continue with the Forge program. But I'd like to sort of take a look at some of the things that we didn't expect, or some of the things that we found intriguing, and some of the opportunities that are applicable for oil and gas and for geothermal. The first one that I'd like to talk about is that we really had very good luck at using deep sonic interpretation, and a number of vendors provide that service. We happened to use Schlumberger in this particular case, and we were very happy with Schlumberger. Tremendous interaction. But what you see from the dipole sonic is a processing of the complete waveform and looking for deep reflectors. And we were able to come up with reflectors that were maybe 30 feet out in the wellbore. And the reason this is important is because you can be overwhelmed by fracturing signatures on an image log. And sometimes we may oversample some of the signatures based exclusively on wellbore measurements. And this really tells you what is happening farther away from the well. And so I think we found it was a very, very effective investment. The other thing that we really made an effort to explore in this well and in other wells is using diagnostic fracture injection testing. Of course, that is standard in the oil patch. Of course, this is a very impermeable rock, and one of the drawbacks of defects in this rock is the length of time it can potentially take for pressure decay. And so we have been aggressively looking at flowback measurements, and a flowback cycle is shown on the panel at the right, where you can do these measurements in a matter of a couple of hours rather than potentially a day, and come up with the same interpretation or a similar interpretation for the frac gradient, and also for transmissibility, KH relationships. One of the things that surprised us in this was a potential rotation of the stress. And from a geologic perspective, it's not inconsistent with the model that is built for what happens geologically in this formation. And this is a really relatively young formation, and their extension is occurring, and there are dike systems and some conjugate joint sets that developed in the early Miocene. And subsequent to that, there has been extension. The extension has established a brittle normal fault in the upper crust. And this fault, we don't know how far down it goes, but it is rooted in some sort of deep myelinitic ductile shear zone. And subsequently, there has been a rotation of the mineral mountains that are to the east of us. And the geothermal prospects lie somewhere in this particular area. And so you can say, hey, there's been some stress rotation that's probably gone on, and it's characterized by an unconformity where the granitoid body is overlain by alluvium. And we blindly assumed for a long period of time that the stress field would still be vertical and horizontal. But we found evidence with unecheloned fracturing in a vertical well that there is potential rotation of the vertical stress field and of the principal stress field, and vertical is not necessarily a principal stress direction. And that's also supported by breakouts that we have seen in the lateral that we thought was drilled in a plane that we presumed included two principal stresses. Now, we don't know exactly what the implications for the stimulation of that are, but we are considering that. The other thing that we certainly adopted and found that was worthwhile in this particular formation was mechanical specific energy. And mechanical specific energy, we had great assistance from Fred Dupriest and Sam Neunert in looking at the energy that is expended in terms of breaking rock. We also want to extend, as people have in the past, using mechanical specific energy, not as just as a representation of dysfunction of bits and BHAs, but also as a representation of the native stress of the rock. As you can see in the far right-hand track, we have a plot in purple, I guess they're both kind of purple, of confined compressive strength and mechanical specific energy. Deviations are an indication of dysfunction, but we're particularly interested in replacing mechanical specific energy analysis just as a dysfunction analysis with an analysis of in situ reservoir properties. Now, historically, this has been done. There's been some really tremendous work that has been done a decade ago by folks at Chevron in terms of doing this, Ross-Evy, for example. But we want to extend this by looking at vibrational analysis and some of the higher frequency analysis to be able to understand want to really exploit the bit as a laboratory. I think this is really important, okay? We can reduce logging expenses, we can pick zones to stimulate, we can understand certainly CCS, the confined compressive strength. We can confirm those analyses with library core and testing that we would do at EGI. But in addition to that, we want to do supplementary analyses of vibration data. And we'll probably do that in conjunction with colleagues at a company called Petrolearn that have had DOE funding to look at high frequency vibration data and infer mechanical properties and in situ stresses. And so there's really a lot of mutually useful data between the geothermal and the oil and gas industry that is being developed at this project, or the Forge project. And we'd like to extend some of that from a geomechanical perspective to understand in situ stresses and mechanical properties further.
So I'm going to discuss some aspects of our program in geophysics that's aimed at geothermal and orogenic scale studies. I'm going to emphasize non-seismic methods that map electrical resistivity structure with integrative interpretations. So resistivity, sometimes referred to by its inverse conductivity, is an independent physical property on par with others, such as seismic velocity, density, or magnetization. And so it offers some unique insights into Earth structure and resources. It's particularly attuned to fluid and thermal processes, and so it's valuable in geothermal exploration and assessment. Will this just... You might have to advance, Dustin. It's with the laser pointer, it doesn't seem to, thanks. So one application here has been in play fairway analysis for hidden geothermal systems in the actively extensional US Great Basin with primary funding from the US Department of Energy. And we've had quite a good team working on this over the past few years. So this view shows several occurrences in Western Utah, including quaternary basalt flows such as Crater Bench, Pavant Butte, and Cinder Crater in here, and rhyolite domes of Twin Peaks and inside the Mineral Mountains that Joe Moore showed. Current producing fields include the Roosevelt Hot Springs, Cofort, and Thermo. Principal barriers in exploiting the resource are identification of permeability and identification of the heat. Surface indications such as hot springs or clay alteration caps are only partially indicative. So study of existing systems geophysically has revealed characteristic structures using our method that indicate both heat input and permeability, and which we will argue may represent pathfinder structures for hidden systems. Next slide, Justin.
Phil, you can actually use your keyboard, the arrows, and it should work for you.
Yeah, that is, okay, thank you very much. So the scale of geothermal resources and their controlling structures is large enough that we need to exploit naturally occurring EM energy sources rather than artificial ones. The natural field method is referred to as magnetotellurics, or MT. Measurements of these fields allows us to produce essentially tomograms of Earth electrical resistivity structure. And so I sometimes call this a solar powered geophysical method. At the higher frequencies corresponding to, say, the upper third of the crust, the sun's energy drives the weather, including lightning activity. So lightning strikes are time varying electric current bursts, and by definition, these constitute broadcast antenna. At longer wave periods, signals arise essentially from variations in the solar wind, which also comprise a regional broadcast antenna. So the propagation of EM waves in the Earth is diffusive, similar to seismic surface waves. So tomographic images tend to be smoothed through the process of regularized inversion. So one powerful aspect of EGI's program is superior 3D analysis of field results. Physical property contrasts for us are strong, orders of magnitude sometimes, preventing low contrast approximations, and the measured data also may be spatially discontinuous, which complicated traditional nodal finite element or finite difference methods. The large scales lead to large element aspect ratios and solution divergences that prevent accuracy. We have implemented edge finite element basis functions, such as in the center here, with direct solvers parallelized on large RAM shared memory processing, or SMP machines here, so large RAM single box systems. They are distinct from the more familiar massively parallel, or MPP clusters used in iterative matrix solutions. The direct tomography solutions follow nonlinear Gauss-Newton parameter steps, utilizing explicit parameter sensitivities, or the Jacobians, which gives us rapid monotonic convergence to tight-fitting models. Edge elements, direct solvers, and parallelization have allowed large problems to be solved on high-end workstations. Of course, clusters of SMPs would be yet another step forward. Geothermal systems form in active tectonic environments, and they're often accompanied by substantial topography. Here we illustrate an advantage of finite elements. With finite differences, topo needs to be represented as a series of stair steps. These cause substantial noise in the simulated E field, as we see in this electrical engineering example here, scattered around a wire. Finite elements allow a smooth representation with no spurious EM scattering. So let's get into the PFA approach a little more directly. So some of our reconnaissance MT profiling that was centered on the Dixie Valley system in west central Nevada revealed a sequence of quasi-tabular deep crustal resistivity zones here. Temperature estimates and geochemical indicators imply that these are melt zones grading upward into exhaust fluids. They are commonly connected through high angle conductors into producing high temperature geothermal systems near surface, which emit magmatic helium-3. And these Dixie structures have been confirmed in full 3D surveying. A separate test was done at McGinnis Hills in 3D, including helium sample from the production fluids in cooperation with Ormat Incorporated, and confirmed the high temperature magmatic nature of these structures. The crustal scale hydrology model of crossionol independently supports this in similar regimes based on spring chemistry and structures. So we're using this discovery, if you will, as the center of a pathfinder approach in play fairway analysis. Western Utah has an enormous amount of excess heat on the order of 5 gigawatts, which is comparable to Yellowstone. We take a multi-criteria decision-making implementation for prospectivity here, where favorability is defined in a tree-like structure, including heat, permeability, and various sub-indicators such as nearby volcanics, heat flow, geochemical geothermometers, and geophysical structure. Now, these are highly disparate data sets and ranges, so prospectivity thresholds are selected, and Krieg probability of locations exceeding such thresholds are mapped. For example, sodium-potassium geothermometry exceeding 200 degrees C. So insets here to the right show some of the low resistivity upwellings that in this particular case conform well to high heat flow. However, many of the heat flow profiles roll over and become isothermal before reaching commercial temperature. So we're trying to use the geophysics to pinpoint the upwelling and to avoid mere outflow areas. Oh, quite a lag there. So at the moment, we have a proposal for about $9 million to the US DOE, which is currently pending, to assess Western Utah more broadly, centering on MT geophysics, well geochemistry, and fault latency. Many indicators show high heat flow and promising fault intersecting trends. The deep source regions for the magmatism are exceeded only by Yellowstone in their anomalous character. And in particular, we will use machine learning, which has a specific role in translating high resolution digital elevation models to fault models, and in gleaning high resolution DEM from lower resolution data sets. The MT method has specifically provided subsurface views of the heat and fluid source for the Roosevelt Hot Springs and the Utah Forge EGS systems. Apparent lower crustal magmatic underplating and fluid release centers under the mineral range. High angle low resistivity projects into the Roosevelt Hot Springs and creates a plausible source for heat and fluids in this hydrothermal system. The adjacent forge area shows very tight high resistivity crystalline rocks, but a plausible source of heat is conduction from these nearby structures. In addition, we discovered one in the north-south section view here, just to the west of Forge, coming up from the northern Milford Valley in and soling into the valley to the west of the Forge system. This is corroborated by high helium-3 contents in well fluids throughout the valley. So we're able to pinpoint heat sources, and also these may be additional hydrothermal systems to look at in the near future. So to shift gears a bit here, part of our research program supported by the US National Science Foundation involves orogenic investigations in extreme environments such as the polar regions. And here's a picture of a field setup that was taken in our Central Transantarctic Mountain project about 10 years back. MT instruments are fancy voltmeters. A magnetic component is measured with high sensitivity solenoids or coils. The electric component is measured with a voltage difference across spans of wire. In particular, in this near insulating snow contacting environment, we needed to build custom buffer preamplifiers in order to break that contact, which is in the mega ohm range and would distort the measurements otherwise. So a specific example of our study is of the active Mount Erebus ultra-alkalic phonolite volcano on Ross Island here, elevation of 12,400 feet, built up right from the seacoast. This lies in an area of active oblique rifting, accommodation, and mantle upwelling, leading to melting, producing a basinite parent. It differentiates through several stages during ascent to a convecting magma chamber several depths below the summit. It's a highly CO2 dominated volcano, the source being a steady stream of CO2 from upper depths that maintains the chamber. There have been imaging challenges in seismology where teleseism has revealed the upper mantle structure, but lack of crustal earthquakes has prevented imaging of magma chamber scale. So the island and volcano we covered with a dense array of about 130 stations jointly supported out of the New Zealand Scott Base and the US McMurdo Base over 3 seasons. These were almost all in place via helicopter transport. There's a well-defined summit plateau here, which we also covered, and a crater with an active lava lake, and deployments as densely as we could practically do. The lower left here is a picture of the finite element mesh here, used to create the tomograms, and with the topography precisely represented, and to honor the EM physics of refraction normal to the slope. This plan view at 14 kilometers depth indicates the magmatic upwelling to and west of the summit. And here in particular, this view of the source region from below the crust into a large scale magma storage zone, and then its entry into the crater. So this abrupt turn, which would be around the brittle ductile transition here, is strongly suggestive of fault valve behavior structure. This is similar to the ideas that Rick Simpson has applied to ore deposits, in particular quartz vein gold systems. Such a valve action could control the replenishment of parental magma to the upper levels through cyclic magmatic pressure buildup and release. This model is very much in keeping with interpretation advanced by Clive Oppenheimer, based largely on crystal melt inclusions, where the parental basinite from 10 to 15 kilometers depth episodically recharges the phonolite chamber. So I'm just going to leave it there. Just a couple of takeaway points here. The high bandwidth of the MT measurements allows source to sync views of geologic processes from scales of hundreds of meters to hundreds of kilometers. The resistivity has a strong potential to contribute where other geophysical properties are transparent to states of interest, such as fluidization. So thanks for your attention, and I'd like to thank the agencies, the US DOE and the NSF.
Okay, Peter.
Okay. Yeah, I'm Peter Rose, research professor at EGI and within the Department of Civil and Environmental Engineering. My group conducts research in R&D into a variety of chemistry and materials and chemical engineering areas, including mineral dissolution, fluid diversion, borehole flow profiling, and materials for zonal isolation. Today, I will focus on another topic, the use of tracers for characterizing flow processes in geothermal and petroleum reservoirs. Tracers provide the best and possibly the only way to truly characterize flow patterns between injection and production wells, not only in a geothermal field, as I've shown here, but in a variety of subsurface environments. So, you know, again, tracers are the best way to characterize reservoirs, fluid flow processes in reservoirs. The tracers are injected either continuously or as a pulse, and then they are produced at production wells, and the concentrations are measured. And they can be then used to show interwell connectivity and flow processes, resonance times, permeability, porosity. And if the tracers are used to calibrate a numerical flow model, then that model can serve to predict future reservoir performance. That's interwell tracer testing. Single well tracer testing is usually, we have developed a family of tracers, the naphthalene sulfonates, and this is the gold standard for geothermal tracing. And these tracers now have been introduced into literally and figuratively into petroleum and other subsurface environments. They have all of the properties that are essential of being thermally stable, non-sorptive, very detectable, available in bulk, non-toxic, and environmentally benign. So tracers are used to trace different phases. And this slide shows a variety of tracers that we have adapted from the petroleum industry and used for geothermal applications. What I'm going to focus on here mostly are the aqueous phase tracers that are represented by the first and last rows, the conservative polyaromatic sulfonates, and then the reactive tracers that in some way interact with the phases that they are into which they are through which they are flowing. Conservative tracers are defined as those that interact neither with the solvent or with the rock through which they flow. Reactive tracers, as the name implies, react either with the solvent or the rock and can thereby serve to measure properties of either, such as effective reservoir temperature or fracture surface area. And it is this latter property that is especially important in unconventional petroleum systems, shale oil or shale gas. But for reactive tracers to be useful, they must be co-injected with conservative tracers. And to emphasize the importance of this, I am showing here flowback tracer concentrations plotted from an unconventional well produced over time at that unconventional wellhead. Shown in warm colors are the tracers that were developed neither to decay nor absorb in geothermal tracer. There are Egi geothermal tracers, and they perform this way also in this shale oil exploration well. Shown in cool colors are the plots of conventional petroleum tracers that were assumed to behave conservatively, but did not. If they were behaving conservatively, they would have overlapped with the geothermal tracers since they were injected at the same concentrations. They were subsequently shown in laboratory flow experiments to both decay and reversibly absorb under simulated reservoir conditions. Their produced concentrations could therefore be misinterpreted since they were assumed to be conservative tracers. And this is a big problem in unconventional tracing universally now in the petroleum world. To illustrate the use of conservative tracers in combination with reactive tracers, I show here some results from an unconventional shale gas reservoir at Dilly Creek, British Columbia. At the left is a plan view of the 10 long-reach horizontal wells, each with 25 stages, not shown. In the middle figure is a plot of tracer concentrations produced over first 6 weeks of flowback. The upper line is that of 1,3,6 naphthalene trisulfonate, a conservative tracer that was produced back from well number 6. The other lines are from conservative naphthalene sulfonates that were produced from neighboring wells. They were introduced and produced from those, and they were introduced in those neighboring wells, but produced back through this well number 6. Also among those conservative tracers, flowback plots is one of our reversibly absorbing tracer. And this then, the plot on the right shows how the use of that reversibly absorbing tracer in combination with a conservative tracer correlates with gas production rates from each well. So this is very exciting because we showed that a reversibly absorbing tracer in combination with a conservative tracer has this power of showing of then correlating with production rate, and you can see then that the tracers can then serve as a useful tool for predicting production rates, gas or oil production rates from unconventional wells. So we have submitted a proposal to DOE that, if funded, will allow us to develop this potentially powerful tool for fracture characterization. The project involves the laboratory characterization of candidate tracers using a novel flow reactor that I've shown here. Fluid is introduced at the top, an aqueous solution containing both the conservative tracer and the reversibly adsorbent tracer introduced as pulses, and they are then that flow is shut in, the flow is reversed, and then the flow is back produced in this reservoir simulating experiment. And shown up at the upper right is a figure of a plot of the flowback concentrations for the conservative tracers in cool colors, and the reversibly adsorbing tracers in warm colors. This strong contrast between the two is confirmed by the field experiment that I showed in the last slide and that I reproduce here at the lower right without the interference of the neighboring wells. And again, the point is that these produced data then can be inverted through various numerical simulation tools to predict well performance. So we are teaming with a company that can synthesize tracers in appropriate quantities and purities. We need more conservative tracers than the 8 that we now have. And we have discovered a family of tracers, of conservative tracers that will add significantly to this list. We are teaming with a tracer service company who will help provide field data and marketing opportunities. Finally, we're developing software that will allow the user to invert tracer data to constrain that all-important fracture surface area. Finally, in conclusion, our group conducts limited tracer testing in geothermal, groundwater, petroleum reservoirs to determine interwell flow patterns. We're not a service company, we're a research organization, but we can do limited tracer testing for geothermal and petroleum companies. We also can consult for the design, implementation, and quality assurance of large-scale tracer tests, either conventional or unconventional. This includes then a short course on tracing techniques. And finally, we have this new initiative that can serve to use this exciting combination of reactive tracers in combination with conservative tracers for predicting unconventional well performance. Thank you.
Hello, my name is Christopher Kessler. I'm the GIS data manager at the Energy and Geoscience Institute. We're going to just go through the Egi Connect Web Application for corporate associate members. To access the Egi Connect system, there's a couple links on our public website. There's one here in the quick links on the front page, and there's also one under the corporate associate program. And I'll just mention while I'm here on the Egi website, under videos, pretty much everything I'm going to talk about right now is also in a video if you need to come back later, so you don't have to remember everything I show you at the moment. There is about a 10-minute video that will review the Egi Connect system at any time you want. Now, knowing that we do have a lot of guests today, and I know a lot of you are not corporate associate members, before I dive into the member-only area, I just want to mention that EGI does maintain the Egi Connect system on ArcGIS Online as a catalog. The URL is egigis.maps.arcgis.com. Once you navigate there, you can just go to the gallery. You'll see all the information we have. And under apps, there's an Egi Connect system available, a web application. And upon startup, those of you that are familiar with Egi Connect in the past, it just looks very similar, the look and feel. There's a lot more capability on ArcGIS Online than we have However, there is a limitation here. This is open to anyone who wants to review our catalog, so you can see the distribution of our data, our catalog. All the attributes are here representing these points on the map. The only limitation is the data behind these points that you would normally be able to get to as a registered user of Egi Connect is not available because this is open to the world, and we're just protecting the raw data behind these data points. But at the very least, you can come in and review at any time our information. You do have access to the project summaries and any abstracts that we have. Those are available to you. So like I said, this is open to the public. Anybody can come in and review our catalog, and hopefully it will generate some interest and generate some questions and help us keep lines of communication open with the industry. So I'm going to go to the member area of Egi Connect. If you're not a registered user of Egi Connect, there is a link on the startup page. The registration is pretty straightforward. Just first name. We do pretty much insist you use your company email address. We don't necessarily allow registrations from a Gmail account or any other common publicly available email system. So we do request you make sure you register with your company email. Security questions you'd put in, you just agree to the user agreement, and you create your account. And upon creating your account, you will receive an email that will verify you. Once you're verified, you can go ahead and log into the system. So before I jump to the map, here's the welcome page. The registered user will see a few buttons on the side. This is just the home page, which will bring you here. Profile, so you can go in and view your profile, update your profile, change password if needed. There are some frequently asked questions. If you had some questions about how Connect works, and there is a user guide as a PDF if you need to download a PDF and review it offline or distribute it among some other people in your company. So I'll go ahead and visit now the Egi Connect system. So the look is very similar as far as the map goes as the ArcGIS Online map. Difference here is you are inside, authenticated and registered, which means as a corporate associate member, you have access to these reports and data. So the red stars are our Egi Connect completed reports, which are available to all current corporate associate members. We also have another category of active Egi projects. And I'll use our oceans projects here as a good example. There's a red star down here, which is a completed report. That's an oceans report. We have one in the Central and North Atlantic that is still in its confidentiality phase. So it's available to sponsors. It'll become available to all corporate associate members, I think, first week of July of this year. And then thirdly, the in development or in progress project down here is as another South Atlantic Egi Oceans project. And that's currently in progress. Soon will wrap up and become available to sponsoring companies. So to access a report, and as you can see, I zoomed in, other points came online. So these are our maps and other publications data. You can click on any one and get some basic information about it. You can review the abstract, and if you like what you see, you can go ahead and download the report. I'm going to show you how the download works for an EGI report, and it works pretty much the same for all the other data. So some basic information about that location, the report I had. There's the project summary if you wanted to read that. If I want to download the project, I click the download button. It's going to go and fetch the file contents of that report. And if you wanted to download the entire report, you can go ahead and click, and that will populate all the checkboxes, and all the data will be downloaded. If you only wanted a piece of the report, perhaps say I only want this integrated geochemistry well summary, perhaps. I can go ahead and download just that piece if I want to. Go ahead and download. It's just going to confirm, going to download. And the processing that takes place, it's putting a watermark with my credentials and my user ID and the date and time and company. That's just, we watermark the reports on a company by company basis just for protection. So once that download, you'll get a notification. I can come here and click on that link. It'll go ahead and download the file. So that'll come into my downloads as a zip file. I can go ahead and open that. And that is the integrated geochemical well summary that I just downloaded. And at the bottom, you'll see it is been watermarked with my ID and time and company. So pretty much all the other downloads work in a similar manner. We don't necessarily go through as many hoops for the seismic and well downloads, but the download system is largely the same. Okay, that's pretty much all I need to go through. I just wanted to reintroduce and even introduce the Egi Connect system to everyone. Thank you.
My job with EGI is Global Chief Scientist and Advisor and also our Euro representative. I've been with EGI since 2019 when I retired from Equinor. I don't be fooled by that nice vista of mountains in the background of my picture there. I'm not in Salt Lake City, as Alan just indicated. I'm in London. I did get some trips visiting companies and one extended trip to Salt Lake City. And then the pandemic hit, and since then I've been in splendid isolation here in London. But at least Zoom helped to solve some of those problems, including training, as you'll hear. So my job today is to tell you a little bit about the professional educational services that EGI can provide for you, that you can take advantage of. So, first of all, Egi Training Services. A lot of companies and even corporate affiliates don't know everything there is to know about these training courses, and it's something you can take advantage of. Short courses and field courses can be provided on request, and they're free to corporate affiliates. Well, that is for covering expenses at least. But one thing that's perhaps lesser known and lesser taken advantage of is that corporate affiliates can actually claim up to a week's peer assist, where you take advantage of the expertise of one of the members of EGI who could have, at least in the old days until the pandemic hit, and we hope in the future, come to your office. But another thing that you can do with that week is to say, I would like one of these courses. And the courses, examples of which are shown in some of these flyers here. So you could say, yeah, I'd like to take advantage of one or more of these. They're also available to non-affiliates. We can do these courses, and if any non-affiliates are interested, any of the courses that I'm going to show you in the next few minutes, just let us know, and we'll try to sort of work up a schedule and what fees it would cost. So usually these courses are provided for and tailored to just a single company. But field courses in particular, rather than classroom courses, multiple companies are possible. Flyers are available for all courses, and you can see some of them here. I'll jump to the last bullet here and say that you can find all of these by just going to the EGI website. And it's easy to navigate from there to education, to field courses, training courses or field courses. And there are flyers for most of these. One thing I want to say, the reason that my own course on exploration, risk and play analysis is at the front here is not because I'm trying to show everybody my ugly mug, but just to say that we can actually do some of these courses virtually. This particular course has been given online to 3 different corporate affiliates over the course of the last year. And although this was a prototype, any of the courses that I'm about to show you can theoretically be done online. We all hope that this is a situation that doesn't continue. We can go back to the better interaction that we have within the classroom. But in the event that's not true, this is something that we can actually do. So again, if you're interested in one of the courses, ask us about whether we can deliver this virtually. It's not quite the same as an in-person course, as I said, but I think what we've shown is that it can work. So this is a list of some of the short courses offered by EGI. I'm not going to go through all of these courses, but I think what you can see from this list is that it covers a wide range. It covers from general topics like evolution of the petroleum industry, introduction to petroleum exploration, risk and play analysis, petroleum systems, and so on, right through to more specialized subjects, like, for example, biostratigraphy, like geomechanics, like reservoir engineering and production in tight plays. So it goes very much from the general to the particular. You'll see there that there's a number of days for each of these courses, and some of these are just ranges. What that basically means is that we can tailor the course to what you need. If you want a quick overview, we can do a one-day course. If you want an in-depth course with examples and exercises and so on, we can go to 3, 4, 5 days for a lot of these courses. So they're essentially flexible. Now, one other thing that you might know about this is that notice about this, sorry, is that most of these are on the petroleum side, on the hydrocarbons wing of EGI. We are also able to teach on CCS, and we're also able to teach on geothermal. So courses like that can be prepared. So if there's something along that line that you're interested in, please don't be shy and come forward, and we can probably do something for you. The CCS is already being taught by EGA members in the faculty at the University of Utah, in any case. And I'd also add to that certainly geothermal comes into some of these courses already. So, for example, Mikhail Nemkok's structural courses, which you see in the middle of this list here, will all consider what the implications are for geothermal as well as for petroleum. And all of these, as I say, can be found on the website. I don't have many slides to show today. This is the last one, but this is basically showing the field courses offered by EGI. Now, as you'd imagine, it's very convenient for EGI to use the wonderful natural laboratory of Utah and the Western US for field courses. And this shows some of the ones that we do in the Paradox Basin, the Rocky Mountains, and the general Utah field course. But from the European side, if you're in Europe or you're interested in European tours, Mikhail Nemkok and his team over in the EGI lab in Bratislava can also do field courses. For example, there's one available in the Western Carpathian Thrust Belt with a structural course, of course, but also geochemical orientation, and in the Vienna pull-apart basin, a structural sedimentological course. So basically, that's all I really wanted to say. I wanted to make you aware that these facilities are available and that you can find out about them from the website. You can get flyers, you can see more information there, or even better, just contact one of us and we'd be glad to inform you about what's available and discuss setting up one of these courses for you. That's all I've got. Thank you very much. And I'd be pleased to answer any questions either now or later on at the end of this session.
Good morning, everybody, or good afternoon and good evening to those in Europe. I'm going to give you a brief overview of EGI's research capabilities. I personally am a senior petrologist at EGI. I specialize in mineralogy and petrology, in addition to remote sensing and geochemistry. So to give you an overview of our research capabilities, we have everything through basic imaging, so optical microscopy, mineral mapping, geochemistry, and then advanced imaging. I'll also talk briefly about our petroleum geochemistry, geomechanics, and petrophysics setups here at EGI. So we like to break it down into 5 different categories. Imaging is one of our main research capabilities that we offer. That goes in hand with argon-argon milling that we can do on samples. Argon milling is very important for things like shales, where you've got soft rocks with complex pore systems. If you mill them or cut them in a standard way, you can actually destroy or deform those pore networks, or you can heat up some of the contents of the shale. And so argon milling becomes very important when you actually want to look at the pore networks in tight rocks. I'll also talk a little bit about geochemistry, and then also about the geomechanics and petrophysics or shale dynamics. So imaging, I've included on each of these slides a publication, and hopefully, as Alan said, they'll be available as a slide deck afterwards. So please look those up, and the authors are EGI authors, so feel free to contact us if you have any questions. So with imaging, we have everything from basic microscopy, so that's optical, so thin section and reflective microscopy, and then mineral mapping using SEM and XRF. And we combine that with XRD. So it's very important to be able to combine both XRD with imaging and vice versa, so that we can get the appropriate amount of clays and quartz. I mentioned briefly Argonai Milling, which is a surface preparation method. And that's key in looking at things well under the SEM, FibSem, and TEM. We can also do things like FibSem modeling, which is where you model those 3D blocks of material, and then 3D phase analysis as well. Geochemistry, XRD and XRF, I've given a few of the sort of basics on both of these techniques. We have both a full-scale and a portable XRD. That means that we can bring it to a well site or a mine site very easily. It gives us very rapid analysis of phases and minerals, and then obviously allows us to make an assessment of things like brittle and ductile behavior. XRF, we also have both a mapping, we have the ability to sort of map cores, so several centimeters, which is very useful for facies analyses, and then also a handheld XRF, which is useful for things like assays. Again, there's a paper that was partly done by EGI, looking at sort of the XRD when it's used in terms of nuclear forensics. Geochemistry, we have the HAWK analyzer, and I've put a paper down there that's relatively recent and authored by Drupad Betty. He's going to talk about machine learning and also give you some more information about the HAWK machine. It's very useful in terms of it provides S1, 2, and 3 and TOC data as well as Tmax. It's very fast and improves the identification of pay and resource plays. In terms of geomechanics, we have the triaxial rock mechanics loading frame. Again, I've put some benefits and values of those of the technique on the slide. It's designed to simulate in situ stress and strain, and that's obviously for the determination of physical properties of geotechnical core samples. It's run by John McLennan, who's already spoken, and here is a paper that will highlight some of the uses of the triaxial rock mechanics loading frame. And lastly, we've got the shell interrogator, which is a high precision petrophysical characterization method, and this is run by Mill & Dev. Again, I've put some of the positives of using the shell interrogator down for petrophysics. So everything from sort of being able to capable of high temperature and pressure studies, which obviously are useful for petrophysical models, calibrations, which other methods can't provide. In addition to conducting evaluations of both liquid and gases in tight formations. And that's it in terms of a brief run through.
Okay, thank you, Brian. This actually puts us about 15 minutes ahead of schedule, which we're not going to try to utilize or use up that time on you today. We did have, 4 good sessions this morning, starting with the VPR and our deans that we work with, and then Millen gave us a great overview of EGI. We had an overview on geothermal, carbon sequestration, and our energy and fluids, and then kind of drilled down on geothermal and had 3 sessions with Dr. McLennan and Dr. Wanamaker and Dr. Rose on using tools and some specifics on geothermal. And then this last session here, we had an opportunity to talk to you a little bit about what the services EGI offers between our database, our training, and then our lab services. So with that, I'm going to turn a little time over to Millen here. He's going to provide us a few closing comments.
Okay, maybe I'll stand up, I guess.
Yeah. Now, tomorrow we're going to start again at 8 o'clock, and we'll go through carbon sequestration. We'll go through some more geoscience, and then focus a little bit on our global studies that we've got, and then future opportunities. So please join us again tomorrow morning at 8 o'clock, and I'll turn the time over to Millen now.
Okay. Yeah, thank you again for joining. I'll nicely summarize the different sessions that we had. I'll just re-emphasize some of the points. We had the Vice President for Research, Andy Weirick, who oversees EGI, and the 2 deans that EGI is closely associated with in terms of academic associations, that is College of Engineering and College of Mines. So the messages there are that the academic community and the administration welcome EGI's role as a research institute and would encourage our academic and research participation at the university. They would like to see this partnership continue to grow for the benefit of not only the university, but also our partners. We are just coming out of the pandemic, as I said, and we want to emphasize the fact that our entire, insofar as collaborations are concerned, we would like it to be a win-win situation, and we would like to emphasize that whatever we do, we would like to take into consideration the needs of our industrial partners. So that is the session number 1. So basically, we highlighted the fact that we have these 3 interconnected areas that very few of the university institutes around the world have. What can be considered traditional hydrocarbon, oil and gas upstream component that, as you all know, in your own companies, things are evolving, things are changing. And again, as an educational institute, we would evolve around those needs. But the fact that we have the oil and gas component upstream, the carbon management, carbon sequestration and capture, and some component of renewables. So geothermal, which fits right into our set of expertise because of our subsurface expertise, gives us a unique advantage of leading that transition. And so that's why we highlighted those 3 sessions with the 3 leaders in those areas, Dr. Moore, Dr. McPherson, and then Russo Sarkoby, who leads our hydrocarbon group now. So what is the advantage of having these three components? It is the fact that we can look at cross-cutting technologies. We can look at cross-cutting science and expertise that can flow seamlessly between these three areas, right? So that's why the next session focused on looking at fracture identification, understanding stress fields, fracture mapping, induced seismicity, which Dr. McLennan covered, some other levels of characterization, the electromagnetics that Dr. Wanamaker, I mean, those are cool technologies, right? I mean, if you look at his mapping, the magmatic field in the Arctic, I mean, that's exciting, I think, from a scientific point of view. And that type of knowledge can flow into other areas, particularly in the time of need like this. And then the tracers, right? Tracers really go into various parts of the reservoir to give you a much better picture of what is down there, which is probably the most uncertain thing that we have in terms of subsurface technologies. So those three, those are just some of the areas that are cross-cutting. There are a lot more, but of course we have limited time, so we just looked at that, and then we finished with some things that are very, very unique to EGI, that are the database that you have at your fingertips. The reports, of course, you have them, but also the data, and that data will become more valuable as we start looking at digital transformation of it and connecting it to other areas in your companies. And then the educational component of the type of courses that we teach, the special courses, but also courses here at the university. And as Tony very nicely mentioned, it is really a geologic playground. That's what Utah is. And we welcome you here as things open up, where people do come from all around the world for field studies here. And then we do have some unique pieces of equipment and capabilities, which Brian highlighted. So anyway, so that was basically the day's program. And tomorrow, again, as Al was pointing out, we'll dig down into some of the science components. We are a geoscience institute, so we have connections with the Department of Geology and Geophysics, and we'll have a couple of faculty from that department talking. Tomorrow, we'll look at data science applications in a variety of fields. Again, we are not going to cover everything that we do. These are just snapshots of different types of things that we are doing, which we hope interest you. But we'd like to hear from you, if not tomorrow at the meeting, but with continued interactions after this meeting. So please keep that in mind. And again, thank you for participating, and we'll see you tomorrow.